Hey, howdy folks, I'm Michael Pyrcz. I'm an associate professor at the University of Texas at Austin, and I record all my lectures. This is part of my undergraduate course on data analytics and geostatistics. And we have, as part of lecture 2, already had a couple of videos, talked about fundamental probability, talked about frequentist-based probability, methods, examples, concepts, operators, and talked about Bayesian probabilities. Got into a variety of interesting applications of using Bayesian probability and how it can be very powerful. Now, when I cover probability, I know a few of my students get mixed up about the issues around probability and distributions, marginal, joint, and conditional. And so this is a supplemental lecture, a very short one, to just cover these concepts. So let's go ahead without further ado. Let's get started. So let's talk about marginal probability and distributions. So you imagine our problem in spatial probabilities or spatial statistics would involve working with some volume of interest in space, and it could be also time. And we have a fundamental problem, and that is at a location within that space, we want to make an estimate of the, say, porosity at that location. And so we could estimate that distribution, treat it like a random variable. It could have multiple possible outcomes at that unknown location, and it goes between 5 and 15% porosity. That entire distribution would be representing a marginal distribution. It's marginal because it's only considering one feature, one criterion at a time, so it's going to be considered to be marginal. Now, if you were to draw a threshold and say, well, I want to calculate the probability over this distribution of being within an interval, that could be greater than 10% to maybe 15% or something like that, you could go ahead and integrate over this continuous distribution and get a probability. Now, that's a probability considering only one criterion, and so it's going to be a marginal probability. Marginal distribution, one event or criterion, and marginal probability when you put a threshold and integrate across that distribution. Now, that marginal distribution could also be discrete or categorical. In this case, we're showing a categorical case in which we have multiple types of facies, and these are shale, fine sand, coarse sand, and so forth. They have an ordering relationship. We could consider them to be ordinal categories. And so the marginal distribution in this case will be the probabilities of being within each one of those categories. Now, if you wanted to talk about marginal probabilities, we would just have to identify one specific category, in this case coarse sand, and say, what's the probability of being within that one category? And that would become a marginal probability. Marginal distribution, marginal probability, continuous. Marginal distribution, marginal probability, categorical. And each one of them could be used to build a model at this unknown location. Now, it turns out that we often work with multiple variables. We're not just concerned about the distributions and probabilities associated with porosity. We may need to work with other features or variables. So in this case, we add permeability, and now our data set will be a point cloud, a scatter plot. We may have even fit to it a distribution, a shape, contours that describe the probability density, the joint probability density relative to both porosity and permeability. Now that is a joint distribution. As soon as we model it like that, it's a joint distribution. It's really the same as trying to fit a continuous distribution in a univariate case. And it's the same thing, but instead we're working with more than one variable at a time. It becomes, with two variables, like a contour plot. Now, if it was three variables, now it's a three-dimensional volume. It's more complicated to look at that. Okay, now if we were to decide on two events, event A is a porosity range between 12 and 14%. Event B could be the permeability being between 600 and 900 millidarcies. And now we're talking about these two events at the same time. Then in that case, I'll just make it clear that that's event B. And now we're talking about two separate events at the same time, and it becomes a joint probability. We take the interval in porosity, the interval in permeability, and now we're talking about the probability of occupying that square in the joint distribution. And we could calculate that, look it up directly from the distribution and get a joint probability. Now you could take the entire joint distribution, bin the whole thing up, and plot and look at the probabilities of being within all these combinations of permeability and porosity. Okay, so now we've defined and talked about a joint distribution, joint probabilities, and even the idea of looking at all of the joint probabilities binned up over the entire joint distribution. All right, so that's joints. Now let's talk about the idea of conditionals. And so imagine we're looking at that joint distribution and we're going to say, well, what's the distribution of porosity given the permeability has some range of values right here? So what we're going to do is we're going to say, nope, we're only working between here and here in permeability. That's happened. We're going to shrink our universe. And now that two-dimensional joint distribution becomes effectively a one-dimensional conditional distribution. It's the distribution of possible porosity outcomes given this constraint on permeability. And so that entire distribution there is a conditional distribution. The conditional probability, really straightforward. All we have to do is assign a interval in porosity, and we'll say what is the probability of that porosity interval given permeability interval shown right here. And we can go ahead and calculate it. Now it's just like regular conditional probabilities as we did them before. We shrink our universe. Now the whole universe is this interval in permeability. We can go ahead and bin the porosity there, get the density, or we could get the joint probability being here, and divide it by the marginal probability of being here to here. Just the basic definition of a conditional probability as we showed it before. Okay, so that's the idea of conditional distribution, conditional probability, and all of this to solve a very practical problem of what's the porosity, permeability at that location right there. Now, how do we calculate marginal distribution from the joint distribution? Now, this is the process of marginalization. And so if we have the joint distribution, the probability density across porosity and permeability, the entire combinations, is shown by this idea of a contour, or it would be a density type map. We look at the definition of the marginal distribution, and we can see that we can calculate it directly from the joint distribution. This is the joint distribution probability density function shown right here. And all we have to do is we would integrate across y to collapse it to the marginal of x. And so it's effectively, graphically speaking, we would simply just integrate over y all of the joints, and that, as long as we integrate between negative infinity and positive infinity, would collapse and give us the specific marginal probability right here. We're integrating over y, and we'll get the marginal probability in x. Or we could marginalize and get the marginal of y by integrating over x. And in that case, we're integrating over x, which is our porosity here, and we're collapsing. It's a summation of all the joint probabilities here, and it gives us the marginal probability over there. So really straightforward. Marginalization to go from a joint to a marginal. The conditional is pretty straightforward too. Again, we have the joint distribution. So we have a representation of the continuous joint probability density function shown right here. We can solve for the conditional distribution just simply by taking the joint and by standardizing it by the marginal. And we showed that previously. This is the idea of just shrinking our universe to the conditional constraint. Y has occurred. Okay, given Y has occurred, now we can bin on Y, and we are going to standardize by that. It's shrinking our universe to that. All right. How do we calculate the joint distribution? What's the process by which we can calculate a joint distribution? Well, how would we get that? And so one way to look at it would be a non-parametric. We would just take the sample data, bin up on the two events, A and B, in this case the two features, and we could simply just plot the scatter plot and count at sufficient resolution. Have bins that are small enough that we can see the features in the joint distribution. This is the standard binning issue we'll talk about when we talk about histograms. Too small a bin's too noisy, too large a bin's too much information is smoothed out, you don't see the signal. Okay, so we just count the points within each one of these cells, and we can go ahead and get a very nice non-parametric representation of the joint probabilities. Taken as a whole, we could consider that to be a bin joint distribution. Now, if we have a parametric model representing the probability density function, we could go ahead and just solve from that parametric form the probability of being within each one of these cells. And so we get the joint probabilities binned representation of, taken together, the joint distribution. Okay, so this was a basic discussion of the idea of probability and distributions, marginal, joint, and conditional. I hope this was useful to you. I also do have a worked out demonstration in Excel. It's on my GitHub account. So if you go to my GitHub account, Geostats Guy, I have a repository, Excel numerical demos. And if you go down, you'll find I have a lot of examples here. I have a marginal, joint, conditional Excel spreadsheet that demonstrates this idea of taking joint frequencies, converting them to joint probabilities to formulate a binned joint distribution, and then from there doing marginalization, summing across columns and rows, not a big deal, to get the marginal distributions and probabilities, and also calculating conditional probabilities and distributions by collapsing your universe. All right, I hope this was helpful to you. I'm Michael Pyrcz again, Associate Professor at University of Texas at Austin. I put all my lectures online. I put a lot of content out on Twitter, my GitHub account. I have a package in spatial, data analytics, geostatistics called GeostatsPy. Check it out, and I'm always happy to discuss. All right, take care. Bye.